All right, sorry for the delay. So like I was telling my in-person folks, just trying to do some outreach events and get those sorted, but policies and procedures always get in the way. That being said, I don't know if you guys are interested. So I used to officially be the advisor of Earth Club, but due to policies and procedures, I no longer am the official advisor, but instead I just help. So I like promoting Earth Club, and even though it's called Earth Club, we kind of generally do more like science outreach activities. So if you're interested, you can join Earth Club and talk to either myself or the officers. So yeah, we've been doing some Boys and Girls Club outreach events and going out in the community. And then had it in lab, but I forgot to make an announcement about it. I don't know if you've seen uh, the Aussies covered surveys going around. They were downstairs. So you should fill out the Aussies covered survey. So if I need to grab a flyer, I can. Like I said, I had it in lab and then I forgot to drag it over here. But basically the history is Aussies Covered started as a food pantry like club out of the Riverside campus. But then I'm not sure why, for reasons above my pay grade and probably policies and procedures, they no longer have Aussies Covered on this campus, even though, I mean, you guys are the highest population. And I mean, unfortunately, I don't know this class as well as I've gotten to know my 200 level students. I mean, that's just by nature because I've been with them like a year at this point. But I discovered that a lot of my students were like either on SNAP or needed food and like needed resources from the food bank. And so I found out a lot of my students in my 200 level class were really struggling since they don't have Aussies covered here. And so I don't know how y'all are faring. But there's quite a bit of you all dispersed everywhere online. But so I would encourage you to fill this out, you know, if not for yourself, your friends. And definitely if you do need resources, then definitely like reach out to people. So Susan Bame is the contact person at RCC for resources. So, you know, if you need like a gas card even or like your car blows up, she may be able to help you get like temporary funds to kind of get you through a situation or connect you with other, like I said, resources. But like I said, I know it's hard out there. And then RCC, I feel like they're sometimes a little dismissive and they're just like, oh, there's resources in the community. But I hear from you guys that, you know, the community resources don't always work out. So just be vocal, let people know what you need. You know, times are hard economically, but you have to make sure your administrators are responding to it. All right, and then we're almost at our last week here. So thanks to everybody who was in lab. And then next week is our lab final. And so you can either take that in person or if you want to take the online version, that's fine as well. Questions? Yeah.
If we take the online version, should we still show up to lab next week?
Nah. Yeah. So yeah, if you want to do that, just kind of let me know. So yeah, I know like what's up. But yeah, that's kind of the plan. We're kind of barreling towards the end here at least. And then any other questions? So next week we still have to do acids and bases, but then final will be week 11. Yeah. Maybe I haven't graded it, but I thought I did. I don't know. I'll go look at it. We can talk after class too. So yeah, help me finish your grades. I've kind of given up on the My Open Math for the end. I just created a lot of work, obviously, and I like could not keep up. So I feel bad about it, but at the same time, I'll just work on that as a side project for next quarter. And I mean, you guys will still get your credit for helping me initially, so you'll still get that 10% different grade scale. So I'll still honor that even though I failed for the rest of the chapters. All right, with that, let's dive into chapter 8. So this is a good one. There's a lot of information, but I think we can pack it in to our 2 hours here. And so this is a good one because it sets us up for like also what the stockroom does. And so this is like, I'll give a little plug, right? So if you're interested in student employment opportunities, then the stockroom could be a future place of employment for any one of you guys, right? So getting your feet wet in lab is a good start. And so then you have to think about, well, how do these solutions magically appear in lab? And so that's kind of our first introduction here is, well, what is our concentration? How do we use it? And so let's kind of look. So, right, we can mix, for example, table salt and water, and it disappears or dissolves, and our mixture is homogeneous. And so these homogeneous mixtures, we usually refer to them as solutions. Again, right, you've seen them in lab. You worked with a bunch today. They could be anything from the indicators. They can be the acids, the bases, right, just in their dilute forms. And then the minor component is usually called the solute. And so that is what you're dissolving generally. And again, for us, we usually think of like our metals or something. I'll just put like sodium nitrate or, HCl, like concentrated, etc. And then our major component is called our solvent. And so for our Gen Chem purposes, our solvent is 99% of the time water, right? We work in a bunch of aqueous solutions. All the the acid, the base, all that is prepared in water. Same thing with any metals that we've worked with, right? Maybe copper chloride or lithium chloride, etc. All those are dissolved in water. And if you go on to OChem, right, then you would use a variety of organic solvents. I'll just name a few like ether, benzene, acetone, etc. We could go on and on and on listing organic solvents, so we won't do that. And so let's look at a colloidal mixture. And so this just means that we have particles of a particular size. And so they're large enough to scatter light, and so this gives us the Tyndall effect. And it also makes our mixtures kind of appear potentially cloudy or opaque, or you can also like hold them up to the light and see them shine generally. And so you can't appreciate that in the picture, but with this colloidal dispersion of gold, like I said, you could kind of hold it up, move it around, and it might be shiny. I don't know if you guys experience that at all with the sodium acetate. I feel like it's not the best example of this, but like sometimes, again, if you get something in solution, then it starts crystallizing out, you start to see this Tyndall effect. And then some examples of colloidal mixtures, so you probably are familiar with them without even realizing it. So you can have these either gas liquid or gas solid dispersions. And so gas liquid would be like fog or mist. And again, right, you're kind of thinking of how the light gets scattered when it's foggy. And so that's the Tyndall effect. Or with like dust or smoke. I don't know if any of you guys are smokers, but maybe when you try to dust your couches, you know, you smack the cushions and then all the dust flies up in the air and starts scattering the particles. So that's the same sort of thing of the Tyndall effect. And then we just have a lot of other examples. So liquid gas, like in whipped cream or shaving cream. You can have liquid, like in paints or mayonnaise. Liquid solid, so you have your golden water dispersion, or again, other paints and pigments. We have solid gas with our pumice stone, and solid liquid with like cheese or gelatin or anything like that. And then solid would be for like ruby glasses or any gemstone impurities there. And so we're kind of building upon our last chapter too, right? I think we had mentioned this concept and it'll come up again. And so we have, right, this like dissolves like, so how things dissolve. And so now we're kind of thinking, well, how, again, does our our salt dissolve in water versus how does sugar dissolve in water? And so we kind of discussed it, but we look at our attractive forces. And so generally, right, they also have to have kind of similar attractive forces. But we can go back. I mean, we've already seen this, right? We're just kind of re-emphasizing. Okay, so last time we said that our water was superpolar. What types of bonding did we see in our water molecule? Good. So, right, we had our hydrogen bonding. So, extremely polar. Okay, so then we have this uneven distribution of electrons. And again, this is essentially stripped. And then, like we've kind of seen before, but again, we're just seeing it again, right? We have, if we're talking about this kind of a little more technically, right, we have our solute-solute interactions. So basically, our electrostatic charges, right, from our sodium and chlorine being attracted to one another. And, right, again, one's a 1 plus, one's a 1 minus. We could calculate that. And then you're trying to see, well, will our solvent-solute interactions then kind of overcome, right, this attraction? And so in this case, it is so, right, where your solvent-solute interactions are able to kind of overcome these solute-solute interactions. And so like we've already seen, the sodium is attracted to the negative end, the chloride is attracted to the positive end, and that's how it works to physically dissolve things. And so then we have these nice, pretty representations. And again, we've seen it, but we're just re-seeing it. And so again, we can imagine our water molecule here. Notice the negative end oriented all around the sodium. Again, that's what causes it to dissolve, right? We have it completely surrounding it. And then same thing, notice how our orientation flips, and our hydrogens are all pointed around our chloride or whatever negative anion we have. And so then materials that dissolve in water to form a solution that conducts electricity are called electrolytes. And so anything that's going to be an electrolyte are going to be your ionic compounds, and then also acids and bases. And so we'll kind of continue this concept in the next chapter. You kind of got a small taste of it today in lab, although judging from the results, I'm not sure that it was quite evident, but we'll talk about it. And then materials that do not conduct electricity in water are called non-electrolytes. And so even though they dissolve, right, they don't have the same charge separation, so they're nonpolar, or they tend to be nonpolar, or but they really are molecules. So, right, our molecules is our discrete package, so they cannot come apart unless, of course, they got some weird acid-base stuff. But for the most part, any molecule is a non-electrolyte, and so that would be sugar. So sugar is kind of our big example. But anything else that's, again, organic and dissolved. And so kind of looking at this, and I don't know if you guys have compared recently how different or the difficulty of dissolving sugar versus dissolving sodium chloride. So which one dissolves easier? Do y'all remember, or what do you have to do with sugar when you dissolve it? Yeah, so stir it around more, or even like a lot of like coffee places and stuff have that simple syrup prepared, right, that they've heated, and so they had to take extra energy to get the sugar into solution by heating it up, and then that's why they present it as a simple syrup, right, so that you don't have, so you're not stirring frantically at the coffee shop. But yeah, so then, okay, with that, we can kind of keep rolling with that idea. And so again, that's why the sodium chloride dissolves more readily in water, because again, it gets nucleated, all these parts. Versus, so we still have the same concept, right? So we still want to overcome our solute interactions, and so we're comparing our solute solvent interactions. And with our sugar molecule, right, we at least have areas of oxygen on here, so that creates, polar regions. And so you can see, right, that our water is attracted to either the negative regions or the positive regions here. But like you can tell from this little representation, right, it's not being dissolved as completely or surrounded as completely as our sodium chlorides, right? So now you're trying to imagine, and so now here's our sugar and the water attempting to surround it, right, and dissolve it. And so again, it does happen, right? So you guys, again, know that it does happen. It's just takes more energy, takes more time, right, to get it dissolved and really, again, overcome those solute-solute interactions there. And so with that, right, the more polar something is, the more hydrogen bonding, then the more likely it will be to dissolve versus nonpolar. And so, right, nonpolar could be completely immiscible, like we've seen with oil and water. All right, so then looking at our electrolyte solutions, and so, like I said, we'll kind of continue this next week. But anything that's a strong electrolyte completely disassociates. And so for our purposes, again, that's our ionic compounds. We won't get into like solubility with this because solubility would factor in, but we won't get that deep. So just any ionic compound, as long as it's soluble, then it's going to completely disassociate into our ions. And again, for our purposes, right, it completely disassociates. And then we'll have a small intro to our weak electrolytes. Weak electrolytes generally tend to be, we'll look at them, but it's going to be our weak acids or bases, but we won't focus too much on bases. And then our classic example for our class is going to be vinegar. And so vinegar will, well, I guess we can get into it a little bit. Well, I feel like I'm kind of covering next week, but I'll give you a preview. So basically, you have this carboxylic acid group, and so that's what's shown here, but admittedly, right, it's hard to tell what show is or whatever. Yeah.
One thing is, why is it written like that instead of like carbon peroxide or hydroxide, rather? I don't know what peroxide. That's it.
Well, it's not a peroxide, even though now I see how you could confuse that. I'm not really sure like why people write these things in all sorts of different manners.
I was wondering why they wouldn't just be like CH2O2.
And you may find it in that form. So that's the thing that students often find confusing is like all these can be written like this or like you said, right, CH2O2. But it's not showing the structure. And so the main thing we want to focus on is like with these funky formulas, they're trying to get at, and so I think that's what they're trying to show here is they're trying to show the carboxylic acid group. But I totally understand. I mean, I see it year after year that students do not understand what the heck those things mean. And again, I don't blame you. But basically, right, we have this carboxylic acid group. And this carboxylic acid group makes any organic a weak acid of varying strength. And so basically what it's saying is it can pop off this hydrogen here. And so then we make this sort of structure, which is resonance stabilized. So then we can move this double bond down here, move the negative charge to the other oxygen. And this is what makes it function as an acid. The fact that, again, you can stabilize through resonance this deprotonated species. But like I said, we'll kind of touch on it again next week. But okay, long and the short, the weak electrolytes are our weak acids or weak bases. And that's pretty much what we need to know for our class. And so looking at other strong electrolyte solutions, so right, sodium chloride is a strong electrolyte, so that's just an ionic substance. And then if something is defined as a strong acid, so like I said, next week I'll have a list of your strong acids, but our strong acids like HCl, so what makes it strong is the fact that it disassociates completely. And so with those, you can draw just a single-headed arrow showing that it's all going to go to completion versus if we were to write the same process for vinegar, we'd want to use these half equilibrium arrows, right? So this is, again, acetic acid, and then it's going to be in equilibrium with its conjugate base, which would be like sodium acetate. So you saw that today in lab. So some of it would be disassociated and some of it would be fully associated still. So that's all that the weak electrolyte is implying, right? So not all of it is broken up. And again, just re-emphasizing our non-electrolyte solutions. So sugar is a molecular compound, and most molecular compounds are non-electrolytes. And so I'll bring the demo probably next week with our acids and bases so we can do kind of the full spread, as I call it. And I mean, you did the light bulb demo in lab, but what we didn't do was we didn't see the difference of a weak electrolyte or a weak acid versus a strong acid. So that's what I'll bring in, like I said, next week for y'all. And then with the non-electrolyte solution, so if there's no ions, right, then there's no way for there to be a movement of electron, and so therefore the light bulb does not light up. But we will see that demoed. So I'll have the sugar water, I'll have some acetic acid, and we'll have some strong acid and compare. And then we can also compare to something like sodium chloride, right, that's fully disassociated. And so basically you can kind of tell from the picture the preview of the demo, but however many ions in solution corresponds to how bright the light bulb is. And so that's cool when we can see it in person. All right, so we've touched on solubility before. And so this is just kind of putting it back in here so we're all on the same page. So right, not all ionic compounds dissolve in water. And so if you kind of think back to the reactions stuff that we did, you made some silver chloride compounds, so those tend to be insoluble. And so you should have your solubility rules on hand. And so here's a summary of the solubility rules. I believe I already gave everyone a copy of this like 1 or 2 weeks ago, but if we need more copies, I can certainly make some more cheat sheets. And so generally how it goes is our alkali metals tend to be all soluble. So lithium, sodium, potassium, and then ammonium is also generally really soluble, so you don't have a lot of exceptions for those salts. And then nitrate and acetate, so those anions are also soluble. So just think about like silver nitrate, right? That's nice in solution, super soluble. And then if we look at our exceptions, well, now we can see where our reactions came into play that we did. So chloride, bromide, iodide. So those paired with silver, mercury, or lead are all insoluble. And so, like I said, I think you've done some silver ones in class. If we need to grab some bottles, we can, but generally you do the reaction of silver nitrate plus sodium chloride, right, to give you your silver chloride. And again, you can do the same thing with lead, lead iodide, and then sulfate. So same thing, most of them are soluble except for the strontium, barium, lead, silver, or calcium. And some of these like calcium, barium ones can be like sparingly soluble, you might see. And so that kind of depends on what reference you're looking at. And so while I'm thinking about it, so I don't want to get, like I said, I don't want to get too into it. We're just reviewing the rules again so we can tell also who's going to be an electrolyte or not. But where you can get like discrepancies in the chart, so any discrepancy comes from kind of this solubility. And so if you look at the solubility, so calcium sulfate has a solubility of 2.63 grams per liter, or this other value. And so if you want to learn more and learn how to quantify this, come take my 200 level course. But that's kind of where these like rules start to come into play and like maybe sound ambiguous or fuzzy. It's because we're not putting a number to them. I was trying to find silver iodide. Where's it? Oh, here's its solubility. And so comparing silver iodide, so silver iodide is much, much, much less soluble, right? So 0.03 mgs per liter with a very small number there. And so, like I said, this is just to give you a little sense of, okay, well, that's why, you know, this is for sure insoluble. Like I said, this one says that calcium sulfate is insoluble, but I've seen other rules where it's like sparingly or slightly, and I just want you to be aware like where those terms come from, and they're not just like pulled out of the air. So like I said, we can quantify it. We're not going to go there. We can just stick with these rules. But if you want to quantify it, take the next level. Yeah. Yeah, so that's sufficient. Yeah, we just follow the basic rules for our purposes. Hopefully you won't run into any cases where like you would be confused as to like what the insoluble product would be. I don't think that will happen. That could be like the only caveat, but yeah, otherwise just go with these rules. And then so just kind of looking at them, right, hydroxide and sulfides are generally insoluble except when they're paired with the usuals, so the alkali metal or a lot of the alkaline earth. And same thing, right? So calcium, strontium, barium, these are all like slightly soluble, so that's where you might get a little confusion. And then if you remember from lab, right, our like calcium carbonate, calcium phosphate, those were all insoluble. And then again, exceptions are with the first row. All right, so let's look at this real quick. And so I'll try to show the rules here. And so just look at these 4 compounds. So lead chloride, copper chloride, calcium nitrate, and barium sulfate. So take a few minutes and predict whether they're soluble or insoluble based off of the rules there. So what do we think about lead chloride? Soluble, insoluble? Insoluble, good. So that was one of our exceptions there. What about copper chloride? So good, soluble. And you may remember copper chloride from lab, right? Nice blue solution. Probably used it for our flame tests. What about calcium nitrate? So good, so soluble. Again, those nitrates tend to always be soluble. And then the last one, so insoluble. So good. So that was, again, I think one of your exceptions for the sulfate. So barium up there. Any questions about those? So as always, right, have your cheat sheet handy. And so then this is just looking at kind of some solubility curves. And I think for the most part, most people know that. And so this is true for most solids. For most solids, the solubility of the solid increases as our temperature increases. And so usually, right, the increasing temperature helps overcome the solute interactions, right, and really break those apart. And then hopefully your solvent solute interactions are stronger. And so you can see that this is true for most of our compounds, right? This is just solubility versus temperature. But we do have one weird exception, at least shown here. There could be more. But for example, cesium sulfate, for some reason, the solubility decreases as the temperature increases. And I mean, I'm not entirely sure why that is, but something with, right, those solvent solute interactions must decrease. as the temperature rises, again compared to like the solute. So a little strange. And then, so now you want to star this, and so probably say gases opposite of solids. And so let's look at that. And so gases are generally have a generally lower solubility because they tend to be nonpolar, right? So the gases are nonpolar, so then they don't really interact very favorably with our water, for instance, right? So again, just kind of thinking about the differences in bonding. And I know we stated it, but I'll state it again. So, right, hydrogen bonding, polar interactions with our gases. And so that means that our gases are more soluble at lower temperatures. And so you can maybe think about this. And I mean, I don't know if we're going to have a soda debate right now or anything. But if you take a cold soda and pour it out, it may not be fizzy, right? Because it's all dissolved in solution still. Versus if you pour out a warm soda, it's going to be all fizzy since you've right now released the pressure valve, and then all the CO2 is going to start coming out at the atmospheric pressure again once we release it. So depending, on how you like your soda, some people do like it all fizzy, but then obviously it's going to go flat right away. And so depending on when you're going to consume your soda and how you like it, you may make some decisions on how to serve it. And so again, just star the point. So our solubility of our gases decrease as our temperature increases. And so then now we get into, well, how do you make our solvent hold more solute? You can vary the temperature or pressure. And so this can go into like canning stuff. I don't know if anybody is a home brewer by any chance or does makes like I've seen this new thing online like ginger soda or something fermentation. I haven't tried it myself, but I was just curious. But basically, or maybe you've seen those. This is another like a TikTok or whatever Instagram video. Have you seen like there's this I forgot what country it's in, but like they serve soda really, really cold so that like they touch it and it freezes kind of instantly, and then they pour it in and it's all this like icy drink. And so all those concepts and all those cool videos that people kind of make on the internet are from kind of manipulating this and being on the border of this saturated or super saturated conditions. And so you can, again, see a lot of that. You can, take solutions, make them super saturated, and then try to crystallize them out. Like I said, that's kind of what was trying to happen with the sodium acetate. I don't know how successful that was or not. And what can also happen, so other kind of examples of disturbing this equilibrium. So of course you can shake a carbonated beverage, right? And that kind of gets you more fizzy. But kind of along this line, what the Mentos is doing. So you guys have seen like the Mentos thing in Coke, right? So they put it in and it explodes. And it generally works better with diet soda. And so part of that is the Mentos just creates this surface for nucleation, right? And then it makes your solution completely unstable, and then your gas is rushing to get out of solution of your Diet Coke. And so that's, again, what causes it to be unstable. And then I think the Diet Coke has more of a pronounced effect since it has extra chemicals and such. And like I said, again, that warm soda tends to fizz more. since it's coming out of solution there. And so with that and with brewing and canning, so you have this temperature dependence of solubility, or excuse me, pressure dependence of solubility. And this is Henry's law here. And so basically, if I were to give you this, I would have to provide our Henry's law constant. And so our takeaway is, right, we have this constant. We'd want to look at the units of this, right? So kind of this is dictating our formula. So it's telling us how much gas we can get in per ATM. So, right, we can fit in 3.4 times 10 to the negative 2 molarity of gases per ATM there. And so we could, again, figure out how much gas we want and can it at the appropriate pressure. And so we just multiply our Henry's law constant by the pressure that we're canning it at. All right, so let's look at this. So this is kind of what I'll call the meat and potatoes of this chapter. And I mean, I think you've, again, gotten a taste of this, right? We've been seeing this whole time in lab, whether we've really realized it or not. So we have our concentrations. Our solutions have variable compositions. And to describe a solution, right, we need our components and their relative amounts. And so that's essentially the information, right, we're getting from the dropper bottles or like from all the chemicals today. So we use what, like a 0.1 molar NaOH solution. So that's telling us the amount. Or like, I think our phenolphthalein, for example, is generally prepared like it says 1% ethanol, water or something on it. And so that's again telling you how they prepare it, right? So they dissolve it in 1% ethanol and then make the rest of water, so just a little bit of organic to get it dissolved in there. And then we also have kind of these general terms of dilute and concentrated. And again, this is just very vague. So generally, I consider dilute to be less than 3 molars, again, just very roughly speaking. And then concentrated tends to be anything greater than 3 molar. And I mean, concentrated just has the general implications as it's kind of more dangerous. So, and again, we've kind of seen that, right? We worked with 6 molar acid before. I think that's the highest molarity we've seen in here. But we just have to be careful, right, that it's more caustic. And then our concentration is, of course, our amount of solute in any given amount of solution. Question? No, just judging. And so this is our, again, kind of cheat sheet for this chapter. So we'll go over all of these in more detail, but we can look at our overview here. So before we kind of look at each one separately, so we'll look at molarity first. So this is the most common one used. This is the one that I'm most familiar with. It's also the one that we use in lab, right? So you see all the little solutions with 1 molarity, 2 molarity. And so that's what this means. And so that's defined as moles of our solute over our volume. But like I said, we'll do some examples, but this is a good overview. Then we have molality. And kind of confusing, right? It's only different by this little L here. And I mean, personally, I don't use a lot of molality. I've heard that sometimes it's kind of used in industry more. But that would be defined as the amount of solute in moles over kilograms of solvent. And so technically this is considered to be more accurate since you're measuring per kilogram. So technically the volume can fluctuate based off of temperature, But like I said, I've always worked with molarity. I've never worked with molality in practice, but should still be aware in case you go somewhere in industry that uses it. Then we'll take a look at mole fraction. Again, we had like a super brief introduction with our partial pressures, but that's going to be just the amount of whatever we're interested in, so our amount of solute in moles over the total moles, so that's mole fraction. Then you can convert that mole fraction to a percent. And then we'll look at other ways that we can describe things. So this could be like parts by mass or percent by mass. We could also throw in like weight per volume. So that's what you're calculating, hopefully today or later on tonight, right, with the acid base lab, that it wants, I think, a weight per volume, if I remember, of the vinegar, right? So it asks you to find, I think, both the moles, but then it's like get the mass, divide it for your volume of vinegar, and that gives you, right, your weight per volume percentage. And so you can do, right, lots of parts by mass or weight by weight, volume for volume, just whatever is stated there. And then we could also do percent by mass, and then we'll look at a couple of others. So our parts per million and parts per billion, and how to deal with that. All right, let's take a quick 10-minute break though before I fry everybody's brains. So let's take a break and then we'll come back at 2 and just resume and keep doing our calculations here. All right, so going back to how you could potentially work in the stockroom or work in industry. And so this is how to prepare a solution from a solid. So we'll kind of go over how to do it kind of physically first. And so, right, again, we have to know kind of how much we're making and the concentration. And again, right, that's what the lovely people in the stockroom do for us all day, every day. And why they're working and always running around since they're preparing our solutions. And so again, right, we might have a 5% by mass solution. So that would be like 5 grams of solute and 100 grams of solution. It's a 5% by mass, so like over the total, over what you're dissolving it in. So like weight per weight. Yeah, no, I get you. And then, I mean, I feel like that's why I like molarity too. So there's like no confusion like that. Yeah. And so if we wanted to go through how we would prepare a 1 molar sodium chloride solution, so right, we have to figure out our amount. And so, okay, let's say we want to make a whole liter then. And so then if we want to make a liter of a molar solution, so that would be again 1 mole per liter. So then we know we need to weigh out 1 mole of sodium chloride. And so that's the first step that you would do, again, kind of physically, right? So you weigh out your sodium chloride, and then you want to add a little bit. And so first you fill it up maybe like 3/4 or so, and then really mix it, mix it, mix it, make sure it's fully dissolved at this point. And then once you're done, then you can take it all the way up to the mark here. And so the other thing about these solutions that's kind of important to understand is they're made in this glassware. So this is a volumetric flask. And so the important thing about these volumetrics is that they're literally only made to measure one amount, right? So this is a 1 liter volumetric. It has one mark to measure 1 liter, and it does so accurately to a certain tolerance, right? And so usually the flask says how accurate or inaccurate it is. All right, so let's look at molarity then. So like I said, molarity is kind of the most used, and we'll see it probably in like the homework. We'll see it in stoichiometry again too. So right, we'll kind of revisit stoichiometry, but just with molarity. And so again, this is how many moles are in our liter. So if we have a 2 molar sugar solution, then we can say, well, 1 liter of sugar contains 2 moles. 2 liters is 4 moles, 0.5 liters is 1 moles. And so for all of these, right, like maybe proportions to work out well. So again, molarity gives us 2 moles per 1 liter. And then you could, right, figure out your proportion like so. So this is a good chapter for proportions. And then, like we said, so next we have molality, which is moles per kilogram of solvent, so still moles. And then, like we said, it's generally considered more accurate since it does not vary with temperature, since it's based off of mass. So again, that's molality with our L for little l, or for little m. So again, moles of solute over kilograms. And so then we have our parts per parts. And so generally it's in the same unit. So right, it doesn't matter. It could be grams per gram, kilograms per kilogram, pounds per pound. And so you can look at your products next time you're out and about shopping. Or it could also be in volume, right? So liters per liter, gallons per gallon. And then so percentage, so right, if we're doing a percentage, then we have a part of our solute for every 100 parts of solution. So if it's 0.9% by mass, then there's generally 0.9 grams of solute in every 100 grams of solution. And then, so let's look at, so parts per million is defined as, right, parts, well, parts in a million. But I always find this confusing in some way. And so I think it's easier if you convert it to your milligrams of solutes, and then you have milligrams over your kilogram of solution. And so if you think about that, right, your milligram, so milligram over kilogram, so milligram is 10 to the negative 3 with its metric prefix, and kilogram is 10 to the third. So then that gives us 10 to the 6 or a million difference, right? So that's how we get part per million. So that's my biggest advice, is convert it to milligrams and then do it over kilograms of solution to help you get your parts per million unit there. And so similarly, I would do the same with parts per billion. So again, we have a 1 times 10 to the 9 factor, and so we can easily, or more easily get that, I should say, by looking at micrograms of our solute over kilograms of solution. So again, those micrograms, that gives you 10 to the negative 6 over kilograms, so 10 to the third again, giving you 1 times 10 to the ninth factor there, so parts per billion. And usually I might pull up the water quality report and we could stare at it for a while. I'll probably keep it moving just in the interest of time today, but your Medford water quality is pretty good, but you can always take a look at it, and that's where you see these parts per million, parts per billion concentration depending on the pollutant. And so then we can do mole fraction, and so it can be, again, whatever mole we're interested in over our total moles. And so it could be just 2 moles or however many moles in the system. And it is unitless, and then we can convert to a percentage. Let's see, I thought I had some practice problems, but maybe let's look at your homework practice problems for this. Let me grab. All right, so let's do probably at least some of the first page of your homework. So we can kind of, well, we can look at number 1 together, right? So we have 10 grams of naphthalene and 500 milliliters of chloroform. And so first it asks us to identify, well, who's the solute and who's the solvent here. So that should be quick. So what's the minor component? What's being dissolved? So naphthalene, good. So this is our solute. And then what must be our solvent? So chloroform, good, our solvent. So that's an organic solvent. And so now go ahead and see if you can calculate. So the first thing it asks for is our molarity. So let's do molarity. And it doesn't ask us for molality, but we could do, I'm just trying to get the density of chloroform now. So let's start with that. So we'll do molarity. And then let's compare molality. But I do have to give you the density of chloroform. So it's 1.48 grams per milliliter. So start with those, and then we'll go over them and continue doing your homework. All right, let's see how we're doing on this. So let's start with molarity. So what do we have to do to calculate our molarity? Need- Excellent. So we'll convert chloroform to liters. And then what's the molar mass of naphthalene? Yeah, you could look it up. The formula was in your homework. I didn't give it to you now. So it's C10H8. So you could either look it up or calculate it. Do we have a number? What'd you get, Aubrey? Let's start with the molecular weight if you have it.
428.17.
Okay, that sounds good. Yeah.
Also, one other side thing, we know how to calculate molar weights. Do you care if we just look it up in the future for homework?
Yeah, I don't mind if you look it up for the homework and stuff, but yeah, just make sure that, like, you're still showing work and at least like give me the molar mass. Like that's fine if you don't show me how you added it, but and I don't mind if you look it up at this point, but yeah, do show some work. Yeah, some people have been a little sparse on the work. I usually don't comment too much, but yeah. All right, so then we find moles. I think I need to pull up my calculator real quick. Sorry. All right, so 10 divided by our molecular weight, so 128.17. And so let me write this moles down because we might need this later. So we have 0.07802 moles of our naphthalene. And then, so now let's finish. So you said convert the milliliters to liters. So that's why I have divided by 0.5 over here. And now I'll punch that into my calculator. And so that should give us 0.156 molarity. So now let's try, I don't know if you got a chance to try molality at all. So we can at least pull this number, right? So we have our moles. So I'll just rewrite this for a second. So 0.07802 moles of naphthalene. So now the next question is, so we said that molality was moles over kilogram of solvent. So C, can we convert our 500 milliliters to then kilograms of solvent and then get molality? So I'll give you guys another minute to kind of try that out. And then we'll go over it. So work through it with me, right? So I have the density here. So again, this was our density of the chloroform. So to find the mass, right, I'll just take the 500 milliliters, multiply it by the density. And so that gives me, well, 740 grams, right? But then to plug it into molality, we need kilograms, so this gives us 0.74 kilograms. And then I'm just going to take this number from before, right, the moles, so I'm not going to recalculate that. And so then we can get our molality. So moles over kilograms, so 0.07802 moles of naphthalene over 0.74 kilograms of solvent. And does that look good to everybody? You'll get the same answer. And then, so let's see our final answer. And so we should have 0.105 molality. And little m. Although I kind of like writing it out so we don't get it confused for anything else. But questions on that one? Did we all get that one? Sounds good. So now let's go back to your homework one. So then your homework then asks for what's the weight, volume, concentration. And so sometimes, right, you also got to like base it off the unit. So we have 10 grams and 500 mils, and that's essentially what it's asking for. So like, hopefully straightforward. So go ahead, plug that in. We'll see our number. And so like I said, this one should be pretty straightforward. We just take our 10 grams over 500 milliliters. And then we should get 2% then. Weight per volume concentration. Oh, sorry, 3 sig figs. And then, well, how do you do 4? Because I feel like the answer key overcomplicates number 4. So number 4 asks us on our homework, so what volume of solution contains 2.7 grams of naphthalene? So see if you can try that. Well, it's asking of our solution. It's just still talking about this same solution. Yeah, yeah, it's just building upon. So it's still the 10 grams per 500 milliliters. And so this one, I think the answer key was like trying to relate it to this 2%. But I mean, just keep it simple, right? You have this ratio 10 grams, 500 milliliters. I would just use your proportion, right? So if you have 10 grams over 500, you have 2.7 grams over X. Yeah. Yeah, so like either way, it's all the same. If you want to use the 2%, I like the proportion better, just because I'm not like thinking about 2%. I don't know. That's just me. It really doesn't matter. It should be pretty straightforward. And so either way, do we get 135 mils? So it looks like yes, so I guess. Or will it be, yeah, well, or finding out, yeah, what what percentage, so like if 2.7 is 2% of what, basically. But I like proportions, so just keep it simple. And so same thing, keep it simple for the next one as well. So how many grams are contained? So now grams of naphthalene and 25 mils of solution. So what would that be? So again, take a minute for that. I'll map it out. So I would just set it up as a proportion. Again, use a 2%, whatever makes most sense. This one might be easier just to multiply it by that 2% in this case. Do you have an answer? Excellent. So zero point 0.5 grams. Let's see it on the calculator. So we could do, again, 25 times 0.02. So that gives us, right, 0.5 grams. Or we can set up a proportion, right, 10 times 25 divided by 500. All right, that looks good. Any questions about any of those or any others? See if your homework. All right, let's look at the rest of the chapter. We'll kind of keep it moving. So the next kind of important part, and slash, again, if you were working in the stockroom, this is what you would also be doing all day, every day. So if you're not starting from a solid thing, then usually you're taking your stock solution. So, right, we purchase concentrated acid. For instance, right, usually you buy it anywhere like 12 to 16 molar is what it comes as. And so that's your stock solution. And then, right, they dilute it down appropriately to make the 1 molar or whatever for our lab purposes. And so this is the formula we need. The C1V1 equals C2V2. And so C is just concentration, and literally the units like do not matter, right? Just as long as the units are the same on both sides. So they just need to be consistent in the problem. So let's see, how can we make that clear? Oops. So units don't matter. but they must match, right? So you could go liter, liter, milliliter, milliliter, weight per weight, parts per billion, whatever, molarity, molality, it doesn't matter. And then sometimes you do see the concentration written as this, or the formula written as this more specific scenario with molarity. But like I said, we don't need to specify. It doesn't matter. It will work with any concentration unit. And so then this is something that the stockroom would do. And so before we scroll down to kind of see the words, so let's figure out, well, what would that volume be? So kind of how it would go. So okay, we need, and I would just call this V2 and C2, right? So we need 3 liters of a 0.5 molar calcium chloride solution. We have a 10 molar stock. How much volume of that do we need to take? So we can set up our C1. And so then we can set up our formula. Sorry, I'm trying not to reveal the answer down there quite yet. So now we have 10 molar times, well, we want to know how much of that concentrated solution we need to make our 3 liters of 0.5 molar. And so now let's solve. So 3 times 0.5 and then divide it by 10. And so then this tells us we need 0.15 liters. So V1 is 0.15 liters or 150 milliliters. And so let's look at that. And so then we would do that. So you would measure out your 150 milliliters. And then you put it in, again, your appropriate volumetric, right? So in this case, you'd be using a 3-liter volumetric. Then you dilute it with water. So you probably want to take it like to 75% again, then shake, 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 and then dilute it all the way to the line. And again, shake it, invert it, get it nice and homogeneous. And I think I forgot to state this before, but if you were to like go past this line, right, you would have to start all over since it would be inaccurate. So yeah, exactly. So that's why it's like you got to start all over. So that's the tricky part of that. But and like I said, now you guys can work in the stockroom, right? And so they would be doing this math all day, every day in there. So let's try that. So to what volume should we dilute 0.2 liters of a 15 molar sodium hydroxide solution if we want to make a 3 molar sodium hydroxide solution? So take a minute for this and then we'll go over it. And this is likely what the stockroom had to do for our lab today. So they didn't make it 3 molar, but 0.1 molar. I don't know yet. Is that what y'all got? 1 liter? Okay, so it sounds like it's 1 liter. Let's go through it together. So we have, we want a 3 molar solution, right? We're trying to get our volume, and we have 0.2 liters of a 15 molar solution. So I assume you got something like that for your setup. So then 0.2 times 15, and then divided by 3 gives you 1 liter. So excellent, you guys all got that. And so again, just to clarify how you would physically prepare it, right? You add your 0.2 liters to a 1 liter volumetric, right? And then effectively add 800 milliliters, right? And so just kind of keeping in mind that this is the total volume and not volume added. Um, so that might come up on a quiz if I do a quiz next week on it, right? It might say like how much do you need to add, and then in that case, right, make sure you are doing the volume added as opposed to total volume. All right, last little bits here. So now we have freezing point depression and boiling point elevation. And so our freezing point of our solution is lower than the freezing point of a pure solvent. And that's what this freezing point depression means. So we're always kind of comparing it to the pure solvent. And so now we're understanding, well, this is why they put salt on the roads, for instance. And so we can kind of think about why this is. So, right, any sort of substance that is in your solution start. Yeah, exactly. So, right, that's perfect, right? So all the bonding, I didn't pull up a picture, admittedly, now of the water, but it basically disrupts the intermolecular forces. And of course, for water, water is trying to make a very organized structure. Oh, come on. I was just trying to Google a picture really quickly, and then I got ice cubes. It's like, I need molecules. Okay. Come over here, window. So I feel like all these are a little crazy. This is a good, there you go, finally got a decent picture. But right, so it's trying to make this organized structure, and then, yeah, anything that we put in there disrupts all this organization, disrupts the hydrogen bonding, and so prevents it from freezing. So that's why you have to lower the energy, right? So make everything stop, and so lower your freezing point. We probably won't do too much with the math in here. That being said, you can at least like appreciate where you could calculate it if you needed to. So it's all based upon this constant. So this freezing depression constant Kf is of course substance dependent, right? So I'd have to give that to you. And then how much the degree with which it's lower is dependent upon that factor, and then the concentration. And then at least according to these units, right, our proportionality constant is given in units of degrees Celsius per little m, which is molality. So, like I said, we don't often see it, and I mean, I guess I personally never use this in practice, so that's why I never use molality, but that's where it is. But like I said, we probably won't do too much with it. And so then, again, the salt disrupts our equilibrium for freezing, so it has to go to a lower point. And so again, we can just appreciate this. we'll skip this for now. And then, so with that, we have, so it's freezing point depression, boiling point elevation. And so this is, I always call it the pasta salt debate. So the debate is, at least in my mind, do you add the salt to your pasta water before or after? And so, like, technically, if you added the salt in before, right, you have to reach a higher boiling point, which some people argue is maybe better for cooking the pasta. But anyways, I'll let you cooks on at home tell me which one is better. And so notice this is also for a non-volatile solute that the boiling point is going to be higher. So non-volatile meaning, right, it doesn't have an appreciable vapor pressure, so it's a solid. So probably a solid here. And then again, right, how much higher your boiling point is dependent upon another constant, and again, times your molality. And then let's see what else do we have. So let's look at the osmotic pressure, because you will at least need to do something with this in your homework. So osmosis just talks about the flow of solvent from a solution of low concentration into a solution of high concentration. And so they're separated by a semi-permeable membrane. And so you have this osmotic pressure, but really we want to put this little I here, which is our Van Hoff factor. And so this is a part that's relevant for your homework. So on your homework, it says something of order your particles. And so that's what it means here. So we want to figure out, right, how many particles it makes when it disassociates. And so a non-electrolyte is, again, one discrete molecule, so it will still be one thing. And so, for example, on your homework, you have a 0.10 molar solution of sucrose, and it's still going to be a 0.1 molar solution of sucrose, right? So it doesn't disassociate into more ions. And then if we look at sodium chloride, so sodium chloride is on here and also on your homework. And so sodium chloride, right, is going to separate into one equivalence of sodium and one of chloride. So if we had a 1 molar sodium chloride, we would have a 2 molar effective solution. And so that means on your homework, where it's a 0.08 molar sodium chloride, you have to multiply it times 2 to get a 0.16 molar effective sodium chloride solution of ions. And then the last one on your homework is a magnesium chloride. So again, same thing, right? Magnesium chloride is an ionic compound, so it should break into one equivalent of magnesium, 2 of your chloride, so 3 total. And so that means our 0.03 molar solution in our homework is a 0.09 molar solution effectively. And so then you just have to order them. So again, increasing boiling points, so whichever one has the highest effective molarity will have the highest boiling point versus, right, the lowest effective molarity. So that's how to treat that part. Well, but it has to do with the concentration, right? So like boiling point elevation, so the higher the concentration, then the more energy it's going to take to boil. And then we want to know these terms. So these terms are important. And so I use the terms in parentheses, at least in chemistry. And so maybe, I don't know if you guys are in bio or anything, but we have either isoosmotic, or like I said, I use the term isotonic. And so that means when we have a solution is the same inside and outside, so there's no net flow of water. And so we're thinking about this in the context of cells. And then if we have a hypertonic solution or hyperosmotic, but like I said, I use hypertonic generally for chemistry. So that means your solution has a higher osmotic pressure, aka more ions, and then your poor cell maybe tries to mitigate that. And so this would be, if you had maybe a really salt-rich, heavy diet, and then versus this hypotonic solution where the solution has a lower osmotic pressure and therefore the water goes inside the cell. And so this would be like the dangers of the gallon challenge. So I'm sure you guys have like heard this before, like a radio. It's usually some like radio station is having people chug water or something, and that could be dangerous, right? Because then you could make a hypotonic solution in your blood, and then you could potentially burst cells. And then obviously, depending on what cells burst, that could be bad there. All right, I think we are out of time, unfortunately. Yeah, the only thing we didn't get to do was these examples, but like I said, I don't think we're going to do them much in this class. So I would just focus on these terms, right? Understanding at least how many ions are created, and then the other math that we did. So I'll go back to this cheat sheet would be helpful. So going back to molarity. And then probably next week we'll do some stoichiometry with molarity. That'll be a good kind of bridge between this chapter and acids and bases. So we'll do acid-base neutralization and molarity. But anyways, on that note, I'll let y'all, like I said, get out of here. I've taken up your time. And then, yeah, questions? So yeah, next week we still have the acid-base chapter, so we'll do our normal lecture on Monday. Well, oh, the final. So next week is the final lab. So we'll do that in lab. So you'll have a little lab if you're doing the in-person one. If not, you can take the online lab practicum. That would be okay as well. But yeah, next week is the lab final, so we get the lab final out of the way. But then we still have our last chapter, and then 2 weeks is our final exam, and you can take that in person, online, or both. So.